So good afternoon from the East Coast to everyone, and good morning for those on the West Coast and everywhere in between. The webinar is going to start in a couple minutes here. I'm just waiting for folks to fill into the lobby here, and then once we hit a good number, I'll start. We should start within a minute or two. Thank you. Okay, so we're going to get started now. Again, thank you for coming to the 1,4-dioxane remediation webinar here. Just a couple of fun facts. And for those of you who are on our previous webinar on Wednesday for in situ chemical oxidation, I'm going to reuse a lot of the same bad jokes. Fun facts are almost never fun when they're used, and these are no different. The webinar is going to start in, we're starting it now actually. All participants are going to be on mute. In about a day, actually on Monday, actually we'll send out a copy of the webinar via email. We'll both have the ability for you to download a PDF copy, and then also we'll have a video recording of it, so you can go to YouTube and view it from there or forward to someone else who was not able to make it. So there'll be that information coming on Monday. The questions, there's a questions panel on the control panel. If you use that to ask questions of the presenters, we'll answer that at the end of the webinar. If we miss questions or there's a lack of time, we will follow up via email after the webinar so that everyone can participate in those questions and we can get those answered properly. So again, this is a 1,4-dioxane remediation webinar. My name is Dennis Keene. I'm a Vice President at XSVE Environmental. I'll be giving the second half of the webinar. I've been in the business for about 20 years now, mostly doing in situ and ex situ remediation. I'm a geologist by education, which means I tend to get a lot of the fate and transport type work at our company. I've done fate and transport for Superfund and Circula sites. And then the second person who'll be doing this webinar, and he'll be going first, is Mike Marley, who is the principal of XTD. He's been doing remediation work since the dawn of time, essentially. Back from the 80s, he was one of the original air sparge implementers, and has also been on the forefront on a number of remediation technologies that we kind of take for granted as standard practice today. So agenda, Mike's going to go through the first half of this. We're going to go through the basic properties of 1,4-dioxane, specifically relative to how it may impact remediation. We're going to discuss applicable remedial technologies with case studies as much as possible, because those real world examples really are where the rubber meets the road. We'll be looking at ex situ versions, advanced oxidation absorption, and some in situ chemical oxidation. We're going to go through some promising remedial in situ technologies. We'll touch on phytoremediation, but not all that much. If you want to know more about that, just because of the limits of time, we can't go through everything. You can always contact us after the webinar. We'll go through air stripping, some thermally enhanced soil vapor extraction, which will also have a case study, and then bioremediation and some analytical methods from microbial insights that might be useful if you're evaluating bioremediation at your site for 1,4-dioxane. So what I'm going to do here is I'm going to switch over and give Mike the microphone here, and then also give him control of the webinar, and we should be good to go. Mike, can you hear us?
Yes, I can, Dennis. We need to go back one. Thank you.
There you go. So you should be able to scroll now also.
Yep. Good afternoon. And basically, as Dennis says, my name is Michael Marley, and basically the dawn of time is actually about 40 years. So it's not that far back. And it's been focused on remediation. And fortunately for me, the involvement in remediation, sort of the late 70s, early 80s, was a lot of these technologies that we are involved with today were developed. So I was fortunate enough to be around for the development of a lot of these technologies and done some research work on a number of them myself. As Dennis said, we're going to talk about 1,4-dioxane remedial options today. And the first slide here, which you can see, is basically just from the Department of Defense looking at a number of their, in particular the Air Force, looking at a number of their sites and looking at the data from a number of the wells on these sites. The pie chart to focus on is the one on the right. And this is from the Department of Defense does funding under 2 programs. CERTUP is more of the fundamental research where they investigate technologies to find out, their applicability. And ASTCP is where they actually field trial these technologies to find out if, to learn more about them with the intent to make documents for the remedial managers within the Department of Defense to make good decisions about remedial options. So the pie chart to the right basically is a summary of the sampling that was done at over 1,600 wells on Air Force bases across the country. And what it's looking at is basically the coexistence of 1,4-dioxane with a number of the chlorinated solvents. In particular, if you look at the early literature with respect to 1,4-dioxane, it has many usages from shampoos through to a lot of different uses, including by itself. One of the biggest plumes in the United States for 1,4-dioxane is unassociated with chlorinated solvents, and it's associated with the manufacture of some medical filters. But as remediation staff within the companies, we're typically more dealing with the coexistence of 1,4-dioxane and chlorinated solvents. The early thinking was that it was predominantly used at high levels, percent levels, as a stabilizer for the transport of TCA or trichloroethylene, ethane, sorry. And basically it, when you look at this pie chart, basically it's not only present where TCA was used. It actually, you can see there, portions of the pie chart show that where TCE is only detected by itself, it's present, where TCE and some of its breakdown products like DCE was present. And the larger slice of the pie chart, the purpley color and the bluish color are associated with the presence of TCA, which is more of what the literature would have indicated. So it's out there in a lot of different sites where chlorinated solvents are present. This introduces an interesting concept in the sense that one of the most common technologies, and Dennis will talk about this in more detail in his part of the presentation later on, but one of the more used technologies, let's say, for chlorinated solvents is biological anaerobic reductive dechlorination, biological degradation, commonly known as reductive dechlorination. What you'll see, and Dennis will go over again in more detail, is reductive dechlorination or reductive technologies in general are generally not effective for 1,4-dioxane. So it raises a conundrum where you do have it, where you basically might want to use reductive dechlorination as a more cost-effective remedial method for the chlorinated solvents present at the site, but they will be ineffective for the 1,4-dioxane. And that's, again, Dennis will go over that in more detail. So looking at some of the basic properties of 1,4-dioxane in the environment compared to some more common contaminants that we would deal with, in particular looking at PCE and benzene, which are very common contaminants. And let's go down sort of the columns here. So from a solubility perspective, 1,4-dioxane is pretty much miscible in water. In other words, it has an infinite solubility in water, which, again, affects its migration in the subsurface. The KOC is basically the octanol carbon, the organic carbon partitioning coefficient, basically is a measure of basically its stickiness as it's moving through the aquifer. And as you can see, 1,4-dioxane has got some retardation associated, but it's fairly minor relative to the like of benzene or PCE. So it is going to move fairly quickly in your aquifer. Henry's law constant is an empirical constant that measures the concentration of a contaminant in the air phase overlying the contaminant concentration in the water phase. The higher that number, the more propensity that the contaminant has to want to be in the vapor phase. So something like PCE, if you're sitting with a container of PCE in water and you measure the headspace above the water, there's going to be a fair amount of PCE in that vapor phase. Because it likes to partition into that vapor phase, similar for benzene. But you can see for 1,4-dioxane, it has a very low Henry's coefficient, which makes it want to be more in the water phase than it would be want to be in the vapor phase overlying it, which makes technologies, ex situ technologies such as ex situ air strippers, not very effective on 1,4-dioxane because the time that you would need or the size of the air stripper you would need to give enough air-water contact to remove it via stripping would be enormous and not economical. You typically don't see 1,4-dioxane as a free product. Its vapor pressure actually is fairly decent with respect to the PC and the benzene. So if it was available in free product, you would expect it to strip off like with soil vapor extraction very effectively. But again, you don't see it in that manner very much. So basically you see it mainly in the dissolved phase because of its very high solubility. The other thing that makes it difficult from a remedial perspective is it has a very low remediation standard and basically subparts per billion. And there's a tendency similar to the PFAS, which is another emerging contaminant of concern. You're seeing a concentrations declining with time. And Massachusetts basically is around about 0.3. I think New Jersey's in the 0.4 level. So basically, it is you have a pretty stringent goal to get to. That again makes it more costly and more difficult to deal with. So again, you would expect to see it in sort of in front of your plume because of the solubility, of the relatively low stickiness or distribution onto the soils. You would expect to see it in the leading edge. The typical question is, well, why don't you see it basically as a sort of slug that's moving off-site? And since it was spilled 30 years ago, why isn't it down like thousands of feet from my source area, and I'm still seeing it at the source area? Well, the reason for that is basically because of the very high solubility and because of the high percent that it was used in some of these products or as a stabilizer in some of these products. When it is released to the environment, it's at very high concentrations in the source area, and because of that, it rapidly diffuses into the lower permeability layers that exist in your soils in the source area, and therefore basically it penetrates into there at fairly high concentrations. And so when the more permeable zones are swept out and moved down gradient, those lower permeability zones in your site then bleed off this 1,4-dioxane over time into the higher permeability layers at concentrations that are typically low in the maybe tens or hundreds of parts per billion level. But if you were able to look into and sample from these lower permeability zones, you would expect to see it at much higher concentrations, so it's bleeding off. So that's one of the reasons that you typically will see it not only as an extended plume, but also in the source area. So let's I've split the technologies that we're going to talk into ex situ technologies and in situ technologies, and let's cover a couple of the ex situ technologies that are right there. So this, with permission from our client, I wanted to use this one because 1,4-dioxane is fairly readily oxidized through chemical oxidation. We'll talk about that in a little more detail, but it is advanced oxidation processes can readily degrade 1,4-dioxane. So if you have a site such as this site, which had a pump and treat system that was ongoing for many years at a landfill, that basically with the emerging technologies coming in and then the request by the agencies to sample for them, you basically get situations where you have a contaminant, a new contaminant that is not being treated by the existing system that was put on, which was very effective for the prior contaminants of concern. So at this particular site, basically it was a pump and treat where the pump and treat was a powdered activated carbon and a sand filtration system. Very effective at removing the contaminants of concern at the time, but when 1,4-dioxane was measured, 1,4-dioxane does not readily absorb onto powdered or activated carbon. Again, there's a little bit of it that will attenuate, as seen by that organic carbon partition coefficient, but again, it's not going to be overly effective. And therefore, basically, we were looking at adding an advanced oxidation process to be considered to address the 1,4-dioxane that was not treated. At this particular site, so if it was just 1,4-dioxane, it was a given that these oxidative processes would be able to take care of that and degrade it down to the target levels. The complication at this particular site, and the reason that I use this example, was it also, you have to be careful when using oxidation processes of byproduct formation or the potential for byproduct formation. In this particular case, there was a pretty high bromide level in the groundwater. And bromide can be oxidized to bromate, and bromate has a MCL or of around about 10 parts per billion. So we had to look at that as part of the evaluation process. As I mentioned before, the reaction between, in this particular advanced oxidation process we were looking at, which was a combination of hydrogen peroxide and ozone, you combine the two together and it accelerates the production of the hydroxyl free radical. The hydroxyl free radical is just a fancy way for a chemical molecule that basically has a very high energy that is capable of reacting with other molecules and breaking them apart. And it's proven effective on 1,4-dioxane. It's not the only one, but it is proven effective. It will destroy 1,4-dioxane. However, bromate, which is a common disinfectant byproduct of oxidation processes, is the conversion of bromide ions basically into bromate. And bromate has that MCL, a very low MCL. So at this particular site, when we looked at 1,4-dioxane and we basically use hydrogen peroxide in combination with ozone, we can, with the proper dosage, we can basically destroy that 1,4-dioxane fairly readily. The problem becomes is that ozone can react very effectively with the bromide to form the bromate. So while you're using the hydrogen peroxide ozone system, you have to look at those ratios. And the ratio that you have to look at is basically you want to produce a hydroxyl radical, so you need enough ozone to react with the peroxide to do that. But at the same time, you don't want so much ozone that you basically end up with converting the bromide to bromate. So you've got a balancing act to do. You could use alternatives to ozone like UV to catalyze the peroxide formation of the hydroxyl radicals, but typically that is a lot more costly from an operation and maintenance perspective. So I want to show you some data, and again, it's a lot of data, but really just what I want to focus on is in this table, we're looking at basically ozone and peroxide at a 1-to-1 molar ratio. So 5 milligrams per liter of ozone is the equivalent to 3.6 milligrams per liter of peroxide on a molar basis. And here you're looking at the peroxide concentration of about 240 parts per billion entering the system. And you can see at the lower concentration of ozone, you're getting a significant reduction, but not nearly enough to get the sub-part per billion level. It requires you to increase the ozone level to achieve that. However, as you increase the ozone level and maintain that molar ratio, you can start to see that the bromate concentration that is formed from the reaction with the ozone and the bromide is starting to get significant and significantly exceed the MCL. So we ran a second experiment, basically. Our second experiment was ran to basically look at a different molar ratios. We looked at a molar ratio of increasing the hydrogen peroxide relative to the ozone. The problem there is basically as you increase the hydrogen peroxide, it actually starts to scavenge its own radical, the hydroxyl radical formation. It starts to basically gobble up the hydroxyl radical and make it less available for the reaction with the 1,4-dioxane. And that's exactly what you're seeing here. As you look at these higher molar ratios where you've got a lot more, peroxide here, you're starting to see that basically the effectiveness on the treatment of the 1,4-dioxane is diminished. You are getting much more effective treatment of bromate or less production of bromate, much more effective reduction in the formation of bromate, but you are getting a reduction in basically the effectiveness in the 1,4-dioxane. So it's a balancing act with the gut. And again, the purpose of these ones were to show you that while oxidation processes are very effective for 1,4-dioxane, there is care need to be taken with regard to byproduct formation. The second sort of ex situ technology that slides provided by ACT Squared, who uses this resin, has a patent on the resin, or sorry, has a license really on their use of the resin. So we talked about the fact that an activated carbon has limited effectiveness because of that organic carbon partitioning, and which makes it the cost effectiveness questionable, because you need a really lot of carbon to be able to remove relatively small amounts of 1,4-dioxane. Shell back in the day developed resins basically for numerous uses in production, in their production processes. One of them is this Ambersorb 560, which is a manufactured plastic. It has a very high adsorptive capacity, and you can also treat it with chemicals to basically also give it ion exchange capabilities. And that's how it's used in some of the other processes, like for PFAS, which actually has ion capacity to be exchanged, and therefore this resin can be effective. But with 1,4-dioxane, basically, it's got that higher absorptive capacity. Dennis, the slides are not moving, so if you could take over and move them, please. Thank you. So this is an example from a site in Florida. Typical 1,4-dioxane in hundreds of parts per billion, well in exceedance of the targets, 100 gallons to 200 gallons a minute. Other organics that were in the system that had to be taken care of, and some iron, which again affects the process. But here, what you see is the influent concentration, as I mentioned, in the couple of hundred parts per billion entering the system. The target of 3, in that particular case, the target was 3 parts per billion. It has been lowered accordingly, but you could see if you move that red line down to 0.3 or 0.4 parts per billion, it would still be effective. And it is effective at removing through absorption the 1,4-dioxane. So that is an option to you. It also is an option that is used for PFAS as well. Shifting to in situ technologies that are available to you, there are a number of in situ technologies that are available to you, and I'll talk about a few of them, and Dennis will take over and talk about some others. So I want to do in situ chemical oxidation. As I mentioned to you, chemical oxidants can be very effective on the destruction of 1,4-dioxane, as well as many other contaminants of concern. The one thing that we learned way back when we were doing experiments with different oxidants was certain contaminants like 1,4-dioxane are not readily destroyed by simple electron exchange from chemical oxidation, such as like with permanganate. It takes more of a complex chemistry for oxidation processes, which produce these radicals that I mentioned. In one case, the hydroxyl radical, which is formed by the combination of peroxide and ozone, and formed by other mechanisms, even by peroxide on its own at higher concentrations. But also basically like sulfate technologies, several different technologies, oxidation technologies that can be activated to form these radical species, which are very effective at destruction of the 1,4-dioxane. So like permanganate, not so much by itself, unless at high concentrations where it was determined in the lab to be effective, didn't translate well to the field. But other oxidants like peroxide to form the hydroxyl radical, persulfate technologies are effective. I added one TCA in here as well for this particular site, for the reason that one TCA is highly oxidized, and it's very difficult to oxidize it unless you produce these radicals. And you also want to produce a reductant radical, which is produced mainly by 2 chemistries. One is high concentrations of peroxide that basically can produce a superoxide radical, which is a reductant, which will be able to reduce TCA, and the byproducts can then be oxidized. And similar with persulfate, in this particular case, when we done the treatability testing, we determined that alkaline activated persulfate would work very effectively, both on the 1,4-dioxane and the 1,1,1 TCA, both through the production of the radical species produced from those more complex chemistries. This particular one was in a fairly silty sandy material in a source area under an operating building, 24-hour operations. Peroxide would have worked too, but because it was underneath an operating building, there was concerns of vapor intrusion and stripping off from the gas production with hydrogen peroxide. So alkaline activated persulfate was selected and applied at that site. And there was 2 applications over a period of about a few months in between. You can see the amounts that were added here. That's not as important to what the results were. But here's sort of like the summary of the results. You can see not only was the TCA, the vertical dots represent the 2 applications of ISCO at the site using activated persulfate. And you can see that the TCA and the 1,4-dioxane basically were reduced to significant levels. The goal wasn't in the source area to reduce these to MCL levels because there was a significant natural attenuation going on from the source area down to the receptors. And so the target really was to get it down to sub-part per million levels. The actual accomplishment, what actually was accomplished there was like an order of magnitude less than that, bringing it down to parts per billion levels, which then were diluted out before the receptor. This site was actually monitored for a number of years post-ISCO, both in terms of metals mobilization, but also in terms of rebound, and in neither case where there's a concern. There is additional oxidation chemistries. There's been research, again, ESTCP, as I mentioned to you, is a Department of Defense funded program. And they have determined that some of these other chemistries can be effective too. In the first case, the first bullet group is associated with these cylinders that basically they're wax-based cylinders into which persulfate and permanganate were added, and they slow release from those cylinders into a system, typically more barrier sort of related type treatment systems. But then when the persulfate and permanganate are released, basically they can react and be effective on the treatment of 1,4-dioxane. Persulfate, as I mentioned earlier, basically when catalyzed to form the persulfate, the sulfate radical, can be effective on 1,4-dioxane, and that was proved effective also. As I mentioned, basically some of the potassium permanganate that should read slow release systems. In the batch experiments that they performed at high concentrations of potassium permanganate, it worked well. But in some column tests that they tried, the release of the potassium permanganate was such a low concentration that it was pretty ineffective on the 1,4-dioxane. So just be aware of that. There's other things that are being tested for sulfate zero-valent iron. Iron is one of the catalyzing or activation methods to form the sulfate radical. And again, it was effective for treatment of 1,4-dioxane, although it was inhibited if too much iron or ferric iron ferrous iron was formed. Other technologies, peroxide-based technologies, ozone peroxide systems. Ozone systems by themselves, question mark on that as to be ineffective or not. I think in the combination with other oxidants, it's been very effective. Other promising ones to wrap up my portion, turn over to Dennis. Phytoremediation basically, which typically does not destroy in situ the 1,4-dioxane, it pretty much uplifts it into the root and leaf system and basically transpires it into the environment where it basically degrades quickly by photolysis, which is again another chemical oxidation process, which quickly destroys the 1,4-dioxane. There's a lot of work going on in this area basically to allow the roots to get down deeper into the environment, to basically be able to draw the waters up that have the 1,4-dioxane in it. There has been some measured destruction in situ in certain cases close to the roots, but for the most part, you're going to expect it to be transpired and removed from the system. The last thing I'm going to talk about before transferring it over to Dennis is air stripping. I mentioned to you before that basically for an ex situ air stripper, the Henry's coefficient, which again is that measurement of the relative concentration in the air phase overlying the water phase, is extremely low. And in an air stripper where you have typically minutes or seconds of contact time between the air and the impacted water, it's not sufficient time to allow the 1,4-dioxane to be stripped. The size of the air stripper that you would need to do it effectively would be cost prohibitive and probably space prohibitive. However, some work that was done by, again, thank you, Dennis. The art is basically a recirculation, in-well recirculation stripping system. And it was, these slides were provided by the founder or the president of that company. What they found basically is when they put, so these wells go into the ground, they recirculate the water with the intent that they draw water into the bottom of the well, they treat it in the well through air stripping, and then the stripped water is released to the top of the well. And this pumping mechanism causes recirculation in the aquifer where you have plenty of contact time, plenty of time for the same waters to go through these wells multiple times. In a typical aquifer, obviously in a fractured rock or in a fast moving aquifer, this may not be applicable. But in this particular case, with a typical slow-moving aquifer, where you've got opportunities to move these waters through a well multiple times, you basically see that over multiple iterations of going through this well, you are getting significant reduction in the concentrations. In this particular case, not down to the MCL levels, but down significant reductions through passing through this system. Now, I done a independent evaluation of the data on this, and what I basically seen was that, move to the next slide, please, Dennis. So what I seen basically was that the mass that was removed in that process, and this is looking at 2 different wells that were in proximity to 2 of these recirculatory wells, that the percent reduction was decent, but on a mass basis, it didn't explain the amount of mass that was brought in versus the amount of mass that was stripped out. And that's because, and Dennis is going to talk about this in more detail, one of the other mechanisms that can be used for treatment of 1,4-dioxane is biological process. Not all biological processes, as I mentioned earlier, not reductive processes, but some other biological processes, and Dennis will talk about that in more detail. And at this stage, I'll transfer it over to Dennis to talk about some of the other technologies and wrap up.
All right, great, thank you. Excuse me here while I just fix a couple items. Thank you. All right, so appreciate it, Mike. So we're gonna next talk about in situ thermally enhanced soil vapor extraction, and we're primarily gonna go through this via a case study where we worked with one of our partner consultants on. So just as an intro to this, I'm gonna talk a little bit about, excuse me, you're saying I'm having a hard time advancing slides. There we go. This is 1,4-dioxane Henry's constant, and this is basically a chart that describes the actual Henry's constant versus temperature here. And you'll notice from Mike's previous, one of his very first slides that talked about the geochemical properties of 1,4-dioxane, he showed the very low Henry's constant, right, which really is just a ratio of the concentration in air versus concentration in water, right? So Henry's constant is very low, so really the 1,4-dioxane wants to be in water as opposed to air. And down at the one section here, right around 25 degrees C, right, his Henry's constant was around 0.0002 or 10 to the minus 4 value is what we're talking about. Just for comparison purposes, Mike also had some benzene, some other items on his previous table, but TC is at about 0.4, 1,1 DCA or TCA is 0.7, and the 1,1 DC is 1.1. So 1,4-dioxane kind of has 2 strikes against it already relative to soil vapor extraction. The first one being its low Henry's constant, and then the second strike being, as Mike had mentioned, it really kind of it really wants to be in water essentially more than anything. So it's really tough to get out. So for this, generally what we do in order to overcome these negatives is we can increase the temperature. And as you can see from this table, we have an increase in the Henry's constant, right? With temperature, we end up about a 13-fold increase when we increase from 20 to about 70 degrees Celsius, right? So this should increase the efficiency of soil vapor extraction at this particular compound. So here's the case study. This is a thermal enhanced pilot test. We had provided modeling and design support for Kennedy Jinks consultants primarily. And the idea is they wanted to do a pilot test to look at thermally enhanced SVE for 1,4-dioxane, just kind of a proof of concept and to understand what the overall cost might be if we're to go to full scale at some point in the future. So our component of the project primarily consisted of 2 to 3 parts. The first part was just a straight soil vapor extraction, right? Since we're trying to enhance soil vapor extraction, we have to get the design parameters for that particular technology down, and we did some numerical modeling for flow rates, vacuum, pressure, pore volume exchanges, and wellhead vacuum and pressure. And this actually is an in-house numerical model that's from, I think it's from the late 80s. It's actually in Fortran, so it's a lot of fun to use. One of these days we will update it. And the only thing I would note here is that we basically determined vacuum pressure distribution and pore volume exchanges, and I could talk about this in an entirely separate webinar, but generally the idea of soil vapor extraction is that you want to bring in fresh, clean air to exchange out the VOC impacted or COC impacted soil gas, right? And sweep that towards wells so you can extract it. So really what's removing those COCs is the fresh air and those pore volume exchanges that occur in the subsurface. Vacuum pressure distribution is often used for soil vapor extraction, but it really doesn't necessarily tell you how much of a fresh air or actual pore volume exchanges you are getting, right? So we tend to like to use the pore volume exchanges to figure out the design parameters for our soil vapor extraction systems. And the second and more relevant part to this project, as far as the 1,4-dioxane is concerned, is modeling via HypeVent XV, and this is a Rob Hinchy model, and it's an analytical solution in Excel, and it'll tell you things like, or estimate heat distribution, your soil moisture changes, your 1,4-dioxane mass removal rates, and also give you some heat input estimates. So this is the SVE component of the modeling, and from that we were able to figure out we needed about 100 standard cubic feet per minute at about 120 degrees Celsius in order to get the pore volume exchanges that we wanted at a radius influence of about 15 feet. And we looked at this over about a duration of 60 to 90 days. The HypeVent modeling, so this is about 15 feet is what this graph is representing, and this is 15 feet from the injection well, right, that is injecting the hot air into the subsurface. And on the y-axis here we have soil temperature, and on the x-axis we have time, right? And as we can see from here, over time at 15 feet we get about a 20 degree or so increase Celsius in the actual soil temperature, and corresponding with that we get a decrease in the actual soil moisture contrast, right? So this soil temperature heat helps us with the increase in the Henry's law constant, and the soil moisture basically also helps us as far as the 1,4-dioxane removal. And then this is the 1,4-dioxane mass removed. So we're looking to see over time, again here, what percent of the 1,4-dioxane mass was removed, and then we have the removal rate right here. So this is the mass removed on a percent basis, and as you can see, anywhere between we're looking at about 120 days here on the far end of the x-axis, and we're at about a 90% removal rate, and then we have this peak associated with the mass removal rate, and then it declines over time. Right, and what we're really looking at is the 1,4-dioxane mass getting removed and our rate decreasing. So after the design component was done, we had a pilot testing setup that was completed, and the design for that was one injection well, right? So that was injecting hot air with 2 extraction wells to extract the 1,4-dioxane as a vapor. We had a number of vapor probe measurements at different spacings from the injection well. The injection was about 100 standard cubic feet per minute. We're using air at 120 degrees Celsius. That was a trailer mounted blower with an inline electric heater. Now, I want to note for this particular line here, you can use other heating technologies, right? There's thermal conduction and also electrical resistance if you wanted to. They tend to be a bit more expensive depending upon the setups. Also, you could use steam at a number of facilities. Steam may be available, especially at manufacturing facilities. But the big issue with steam is while it has a very good heat density relative to just air, you're also adding moisture into the subsurface, which can help defeat the process that you're trying to do here. So the 1,4-dioxane will be less efficiently removed with steam potentially than hot air. And the testing was done over about 77 days at the site. So, and this is, I understand, a very confusing figure, and I apologize for it. It's one of the only ones we had, but we have our injection location here in the center and our two extraction locations here on the edges, the radiuses, and we have a whole number of proposed vapor probes and temperature probes located in between, so we could understand what was happening in the subsurface during implementation of the pilot test. So the results. So we had the majority of lateral temperature increases in the shallow. They were around 4 to 6 feet. In the deep, they were about 8 feet or so. And this may be due to insulation in the shallow subsurface. You may not have nearly as much insulation as you do in the deep relative to soil and surface cover. So you may have losing a little more heat there. The model itself, the HypeVent model, provided an excellent prediction of soil drying adjacent. But as with any subsurface, you're dealing with potentially heterogeneous distribution, right? So as you get farther and farther away from that injection well, right, the heterogeneity kind of compounds upon itself, and you end up with a little bit more variability as far as the soil drying is concerned. The actual goal of the pilot test was really to look at how much 1,4-dioxane was removed by. So the 1,4-dioxane was removed at about 80%, and that was measured about 11 feet from the injection well, and that was about after 77 days. So it hit pretty well relative to the actual modeling itself. And then the overall concentration reductions ranged anywhere from 58% to 97%, and those were all measured between about 12 and 32 feet below ground surface. I'm going to move on to bioremediation now. So this is, as Mike had mentioned, we have a process here, aerobic and anaerobic. I want to talk about the aerobic process first, which is in the presence of oxygen. There's a number of organisms that use 1,4-dioxane as an energy source. It's more effective at 1,4-dioxane concentrations that are very high, right? They're not very good at low concentrations, so you really kind of need a good amount of 1,4-dioxane to use as the energy source at this particular point. So you're not likely going to hit very low levels, you know, in the sub-part per billion ranges using just 1,4-dioxane strictly for bioremediation. There is a co-metabolic process, right, which is slightly more effective at getting to lower concentrations. And that essentially uses an aerobic process where you're degrading THF, propane, toluene, or a number of other simple kind of hydrocarbon type compounds, right? Essentially, the big issue here is that those primary substrates cannot be too high, right? So if we have those concentrations exceedingly high, what ends up happening is the microbes are really just using the substrate as an energy source, and you're really not getting the co-metabolic benefit of the 1,4-dioxane biodegradation. And then in a number of instances, you may need to do bioaugmentation, right? So you may have the necessary 1,4-dioxane microorganisms down in the subsurface, but may have a difficult time growing them. So often if you do bioaugmentation, right, you can basically increase the overall cell mass, and that helps you as far as getting the rates you need to achieve for your degradation product. The big thing for 1,4-dioxane bioremediation is chlorinated ethenes, especially 1,1-DC can inhibit the biodegradation of 1,4-dioxane. Recently, there was a study done that looked at a particular bacteria that can degrade 1,4-dioxane and 1,1-DC, but the real issue here is that you need to basically degrade all of the 1,1-DC first prior to getting to the 1,4-dioxane. So it really is kind of a sequential step here. Metals can also inhibit biodegradation, copper, cadmium, and then most of the activity here is associated with monooxygenase enzymes. Anaerobic. So anaerobic, there's not a lot of evidence relative to the anaerobic degradation of 1,4-dioxane. Laboratory experiments back in 2008 showed that there was bacterium associated with a sludge and some humic acid additions that could degrade 1,4-dioxane anaerobically, but there really weren't any significant field observations. In 2015, there were some microcosms done that actually went for a pretty long time. There were about 4 years of incubation and didn't see any degradation of 1,4-dioxane. I suspect part of that also is due to some of the chlorinated solvents that were located in those microcosms. As we mentioned, the ethenes can inhibit the degradation of 1,4-dioxane. So this is a case study from Lippincott, and so this goes into excuse me there. So this is microcosms that were done prior to a pilot test out at Vandenberg Air Force Base. And the microcosm was looking at what type of setups you would need in order to degrade the 1,4-dioxane. And this graph can be a bit confusing, but if you look here, essentially all you need to know is all the other test conditions are up in this location, and there's a singular test condition here that showed degradation. We have 1,4-dioxane concentration on the left and time down here on the x-axis. And that is associated with this bioaugmented version of particular microorganism, right? So in this particular instance, what they did is they used oxygen plus propane and then did a bioaugmentation to see that they get the degradation they needed. And if you look at this line here, if you want to understand what the half-life is here, we're looking at a half-life of approximately let's say about 120 days at this particular location, right? Until we get down to concentrations that are very low, at which point we have a spike here, which is essentially a respike. They ran out of 1,4-dioxane to degrade, so they respiked it in the lab. And you'll notice that our half-life is much, much shorter in this particular instance. So what's happened here is you have quite a bit of acclimation already. Basically, you've gotten the cell mass growth so that you can basically degrade the 1,4-dioxane reasonably quickly. And acclimation can sometimes be deceiving, especially early on when you're doing these microcosms. If you had stopped your microcosm at this particular location, really it would have been within this noise that showed kind of no degradation. It really takes a while for that to kick in properly. So based upon the microcosm, they went to a field pilot test, and there was they did a 1-month air sparge, which was a control phase, right? And there was a 45-minute pulse per day just to see what conditions would look like prior to adding propane and bioaugmentation. They did an optimization period, right? And this is what we talked about with the acclimation. They did about 40% of the lower explosive limit for propane, which is about 0.83 pounds per day, and they cycled it about 6 times per day. They did the bioaugmentation similar to they did in the microcosm. On day 42, they added some nutrients, and then they did some performance monitoring. So here's the field pilot test results. A couple of things to note here, and we have this table here that shows the actual day 14 concentration, day 45 concentration, the percent degradation. And as you can see, for the vast majority of these locations, they had significant degradation, right? So relatively successful. There was a couple of locations that did not do nearly as well. I'll specifically point out 5B here, and then also 34B here. So this green line on this graph is essentially the radius of influence associated with the sparge well located in the center here. And it just looks like 34B here was close enough that you were getting some pretty good distribution of the propane and the oxygen, and then also the nutrients, whereas 5B, which is on the edge also of this radius of influence, really didn't do quite as well. So it's really just a question of spacing and some heterogeneity associated with the subsurface in this particular location. So reasonably successful pilot test. And then this is really interesting. This is a SERDP study, so that's the Strategic Environmental Research and Development Program. It's a DoD project that does research associated with innovative and remediation projects or innovative remediation technologies. And what they did is they looked at a couple of different data sources. They looked at the California GeoTracker and the Air Force sites and tried to figure out 1,4-dioxane, whether or not the trends were increasing or decreasing, and in what instances they were increasing and decreasing. So for the California sites, they looked at about 193 locations. And of those 193 locations, 30% had statistically declining decay terms, right? Which means 30% of those locations were going down. The alternative way to look at that is that 70% of the sites had no source decay term, at least not significantly, statistically significant, right? So in those instances, we really weren't seeing that much. Of of those 193 sites, about 23% had an order of magnitude reduction, right, in the max versus recent dioxane levels, right? Very few had 2 or 3 orders of magnitude reduction. So what that really means is if you have 100 ppb in groundwater, you know, you have a good chance potentially at the sites that do have a source decay term of getting down to, you know, 10 ppb, but you're really not going to get down more than that relative to the data from the California GeoTracker study. Air Force wells. So of the Air Force locations, there's about 441 of them. And those are reasonably similar, or almost exactly dead similar to the California GeoTracker, 30%. 70% of them had stable to no trend, and there was about 9% of those had increasing trends. So very, very similar. Of the Air Force wells, it was a more robust data set, so they could look at a few more parameters, right? They found that, you know, of those 30%, the attenuation rate was positively correlated with dissolved oxygen, right, which is what we talked about earlier with the aerobic degradation process being the primary pathway, and then negatively for CVOCs, and again, 1,1-DC in particular, and metals being one of the larger ones. The median half-life for this was also about 20 to 48 months for the statistically significant attenuating sites and wells. And then, so for the biodegradation here, there is some analytical work that you can do relative to biodegradation to show that this is the primary process by which you're losing 1,4-dioxane, and it isn't something like dilution or some other kind of a non-destructive pathway that could be reducing your 1,4-dioxane concentrations. And the first one is a compound-specific isotope analysis. And we're really just looking at stable isotopes associated with carbon. You can look at for chlorine and also hydrogen. And this can show definitive proof of degradation, right? When you have biodegradation occurring, you can selectively select for certain stable isotopes, and you can look at those ratios relative to your source areas. The nice benefit of this is you could also potentially prove multiple sources depending upon the source of the 1,4-dioxane and whether or not they started with separate stable isotope, or I'm sorry, specific isotope ratios. The detection levels for the 1,4-dioxane for that are about 1 microgram per liter if you use the carbon 13, and then for the hydrogen 2, it's about 20 micrograms per liter. The other item that you can do is the qPCR. Really what you're looking for is the genetic markers for different enzymes, dioxane monooxygenases. You can look at methane monooxygenases, and then there's some short chain alkane monooxygenases also that you can get. And then stable isotope probing, we've actually used this at 1 or 2 sites in the past, and it's actually a pretty neat way to look at biodegradation at your site. We actually used it for anaerobic degradation of benzene, but really what you're doing is you're getting a C13 labeled 1,4-dioxane trap that you can basically put down into a monitoring well, right? And then essentially as your microorganisms are degrading the 1,4-dioxane, the radio labeled C13 acts as a tracer, and you can look at it in the biomass and carbon dioxide that comes off of the when you do the analysis. And that's pretty much it. I think what we're going to do now is I'm going to look at the time here really quick, as it's 1:52, so we have a little bit of time for questions here. I'm going to pull up the questions to see if we have any, and then Mike, if you take yourself off mute here, we can go through these really quick.
Yep, I'm here.
Sure. So Mike, when you were talking about the extent of the plume from the source area, why aren't the plumes more extensive? The question is if the back diffusion, right, is in the 10 to 100 ppb level, and the 1,4-dioxane isn't breaking down or absorbing onto the soils, you know, what's controlling the size of these plumes? Is it mostly dilution?
Well, again, I think on terms of the size of the plume, obviously the hydrogeology's got a big impact on that in terms of the groundwater velocities, etc., and the time of the spill. You know, you see everything from groundwater moving like a foot every 10 years to like several hundred feet in a year. and obviously you'd expect to see elongated plumes under that scenario. Eventually, as you go further out, I think, yeah, these, as Dennis pointed out in his last couple of slides there, if you get to the edge of a plume where there's oxygen available, and basically you have something else in your plume, say for example you had toluene or something else that was in the plume, there's dilution mechanisms, there's dispersion mechanisms, there may be some biological going on under that at that boundary where there may be oxygen present. Again, the overall length of the plume is going to be probably dominated by the hydrogeology and how fast things are moving.
Okay, and actually I think that's the only question we have, Mike. So again, I want to thank everyone for coming to the webinar. Again, as I mentioned in the beginning, we'll be sending out an email on Monday, and that'll have a link to this webinar and the recording, and you can download that from the email that we send you. And if you have any additional questions at all or would like to contact Mike or myself, please feel free to do so. And enjoy your weekend. Thank you very much.